This meeting is being recorded.
What happened?
If you want, what is the material today? If you want, okay.
Is that okay?
Okay, yes.
All right. Okay, finally we can start. Hope everybody can listen me. Yeah, hope now you have a solid understanding about combinational circuits and sequential circuits, and we have already discussed quite in lengthy form. I hope now you know the differences between combinational and sequential circuit very precisely. So as we understood that really involved with the clock, whether it is really connected to the first we know that asynchronous and synchronous, and then we know that really combinatorial circuits or combinational circuits, we basically design really several different types of digital. Can you hear me? Can you hear me? Can you hear me?
Yes.
Yes.
If you want, if you want the presentation, I'll share the presentation.
This is not in the presentation mode.
Yes, the same presentation.
Okay.
If the connection bandwidth is not too good for you, I'm the share screen. I can share the screen, and you can explain. Yeah, if you don't mind, sir, if there's a bandwidth problem or connection problem, let me share the screen. I also have the presentation.
Let me.
It seems that the mic and the has a feedback on your side of the end.
think I have another mic nearby. I can't find any mic, any speaker. So
Oh,
I don't know. I have only computer. Unless otherwise, let me check. Rudy,
yes.
can you stop? There is another Arosha Senanayake here. As a user, can you just take it out?
I cannot hear.
I will type here.
Can we
There
use
is
chat? Chat.
user called Arosha Senanayake. Please remove.
Please wait for a moment.
Hello, can you hear me
Yes.
now?
Yes.
Okay, good. Right. So we can start now. I
Okay.
hope everything is good. Hopefully. Let me see. Now it's okay?
Okay. This is okay.
Hello?
Yes.
Is that okay?
This is okay, sir.
Okay, good.
The sound is
So
okay.
let me start.
The screen is also okay.
All right. So everybody can hear me, huh?
Yes.
Okay. So that's silly. You have already understood very clearly combination circuits and sequential circuits. So then how these types of circuits involved in digital system design. That is one of the key things you should know. But in terms of designing these type of digital systems, we require to understand what type of digital systems you want to design. So there are different types of digital system design, FPGA and so forth. But all in all, you have to know fundamentals behind so-called computer architecture. What is the meaning of computer? Any digital system you design should be capable to process data. Process data means process data and how the execution of instructions given by user, so that really processing data and sending data to different we can call elements require the
Sir, your connection is breaking up.
controllability of data. Speaker.
So sorry, Dr. Arosa. Your sound is not hearable. Your sound is missing in our end.
Hello?
Hello, sir.
Hear me now? Can you hear
Yes.
me?
Yes.
Can you hear me?
Yes.
Can you hear me loud enough?
Yes. But the connection on your end is on our end is also lagging. So
No, now lagging because now I connected to a different network.
okay.
Still lagging.
No.
Now we are in a different network.
Oh.
It's still lagging.
No, I can hear your sound clearly, but the video is lagging.
Video. Okay, I haven't done anything to the video. I mean my movement. My movement.
Yes, your movement and your sound
My movement is lagging.
is now lagging.
No.
Okay.
Let's see. Again lagging. How is that now?
Okay. If you don't mind.
Hello.
Hello, sir. Hello, sir.
Yeah.
Yeah. If you don't mind, if I share this screen.
Yeah, I can hear you.
Yeah. If I share this screen, can you see it?
Okay,
Can you
yes.
see? This is
I
this
can see you.
yes.
I
Is
can
this
see the screen.
okay? Okay, you can see the screen. What what page do you want to this one? Starting from this one?
Yeah, now we go to the second page. Of course, now we are late. We go to the
Okay.
second one. Yes, introduction.
Database.
Okay.
Okay. If you want,
We go to
let me
yeah. Okay.
let me the one who presents. And
No,
you,
no.
if you want,
You
you can go
go one
next.
before. Better.
This one.
One before.
This one. One after this.
No, one before. That's one. Okay. Just
The
no. Okay. And now you
now
next one.
your connection is still
Yeah.
this the connection is
Right.
not clear.
Right. So then, yes, I was telling you a short while ago, of course, when it comes to execution of tasks by a computer system, really, of course, we have to somehow look at it, number of tasks. Is that so? What about if I, how is like that now? Is the connection now is good?
It's good, sir.
Can you hear me?
Yes, sir, we can hear.
You are mute. You are mute.
Yes, I can hear you. I can hear you clearly.
Yeah.
Okay.
Can you hear me? Is lagging again?
Yes.
Lagging.
Yes. The sound is not clear. Still lagging on my end.
Let me see any problem. Okay, then. Let me see. Is that not clear still?
It's for the sound is clear.
Now is clear or lagging or what? Again.
Yes, this is clearer. More clear.
I mean, my sound is little again. Volume
It's
is
A bit lagging, but we can hear you.
Hmm. What shall we do? Can I continue or what?
Yes, you can continue. It in what page that you want me to
No,
show,
no.
or
Now it is correct.
Okay,
The page is correct. Whether we
the
can
page is
continue or
correct.
not.
Okay, please
Yeah.
continue. Yes.
Can we continue?
Yes.
Okay. All right. So then, yes. Then, of course, what happened that, as I told you in the previous slide, we have to execute different tasks. So not just one task or not a single task, different tasks we have to execute. Then actually we require processing different types of tasks simultaneously, but computer or processor is not capable to process many tasks simultaneously as far as you have only one processor. If you have multiple processors, yes, you can execute multiple tasks. So then actually we should be able to, as the user, we should be able to control such a way that the data are processed based on our needs. So then thereby, yes, computer defines really taking into consideration set of instructions and such and ways we can direct processor to execute the way we want. Of course, the way we want. CPU is not capable to really analyze what we want to solve, but only thing is we have to provide, certainly you know very well now, algorithms, and then at the same time really, yes. So then in that way, whenever a CPU is designed, they will take into consideration two important things. One is the instruction set architecture used really for the computer architecture already model. So then actually any hardware CPU design based on really the architecture and the instruction set architecture, really dealing with the system architecture of computer architecture. So then in terms of really data path, of course, whenever we ask really computer to process a task, actually then processor is required to do the processing, taking into consideration the way CPU understand in a CPU speeds and not that really the user speeds. So whenever really you enter data using a keyboard, it is too slow for processor will be idle for most of the time. So therefore, of course, really inside the processor you find a set of registers which are temporary storage, which is constructed particularly using such as you learn really flip-flops. So then flip-flops, D-type flip-flop or JK flip-flops. So then, because you know very well that really they are really storage devices, storage elements. So therefore, of course, we can use registers, but not like really you are having a RAM inside the computer. So then you know that the RAMs in a big like now really, of course, you can say that the RAM is like 64 gigabyte and so forth. So then, but unfortunately, inside the processor, if you want to put that number of registers, it is going to be really big. Why? Because of really data propagation. Data propagation inside the CPU is limited, taking into consideration number of bits used really for the architecture. So then, therefore, we have to look at it. Registers depending on really number of bits of the processor. So then depending on that really what are the operations, so normally micro operations can be done, and what kind of control we have to have really design inside the CPU in order to control from one side the execution of a task, for example, addition, subtraction, whatever, using ALU, and on the other hand, how the data really propagate from the CPU to the outside world, and so forth. Of course, we can move to the other slide. Please move to the other slide. Probably I can share now. Yeah. So then, in that, of course, you can see that we have a simple data path. Really, of course, as you can see that we have here. You can see 4 registers. We have 4 registers. We have 4 registers, and therefore, of course, really, in this case, what we can do that we can store really 4 different values. 4 different values. Let's assume 4 different values, but it depends on the number of values it can be stored based on the bits. Really, we can really store inside the R1. So if at all really it is 1 bit, so that means really only you can store 0 or 1. 0 or 1. So then we have really 4 registers. So then, interestingly, if you look at closely, so then we have really bus A and bus B. What are those? Of course, really bus A, if I'm not mistaken, it is here. Am I correct? Bus A and bus B, I cannot see properly. So then take really 2 register values really as operands, and send to really process by ALU, for example. So then results will be stored really in another bus called D. So then therefore, of course, really bus A and bus B bring operands. Operands means, for example, A plus B. A plus B. Add whatever in A with B, and result of the operation will be placed in bus D to propagate that data into the outside world. Of course, before being really propagated, it will be stored in a register, and then later on really use a bus really to communicate with the memory and as well as really input output devices. So then this is what we have seen here, is that how it is executed within the processor, using in this case, for example, this is ALU, arithmetic logic unit. So interestingly, then you have to understand very clearly how the data are propagated. So then in that sense, of course, you can see that there are a few important combinations we use. From one side, you can see the decoder is used. Decoder. So depending on really the selection of registers, so then of course really you have to use. So as you can see, there is a decoder. So then, so in order to really, of course, send really the result what we can as well. So then, on the other hand, of course, really you have seen A and B. Of course, taking into consideration what are the values to be added, and subject to, of course, really the operations that can be carried out by the arithmetic and logic unit. So then arithmetic and logic unit, so then in that way, of course, you can see that we can really process different types of really execution, such as addition. So then in general, what I want to tell you that really here, decoder and multiplexers are involved. Of course, why? You have to understand the fact that really at a given instance, so then we want to really take out really from this really output of the multiplexer one of these combinations, depending on the A select and select. So then we have to take really the values coming from R0, R1, or R2, or R3, or R4, and process the data accordingly, so that really the execution will happen. So then, yes, just to give you an idea about it, how really in general, then what we have to understand that really, yes, when it comes to arithmetic logic unit, yes, You would have already understood, I'm pretty sure, that during combinational circuit design, so when it comes to ALU design is more or less really you understand that really chain of adders you connect, so that really you will get really completely done depending on the number of bits required for the ALU. Of course, you can have it. So, for example, in this case, of course, really, we clearly understand that really this arithmetic logic unit takes really n number of bits. So then through A comes really one operand, through B comes another operand, and do really, for example, an addition, and then produce an output and goes through really a G0 to Gn minus 1. So then n bit. But when it comes to addition, if at all really, we have already understood also during the adder designs, we have full adder and we have half adder, and we have noticed that really carry in and carry out. So then precisely, I'm pretty sure you would have noticed that. So then in that manner, of course, really, we can use carry in, and then I'm not going to explain again carry in. Of course, you would have really understood that. So then the carry out, and of course, really, sometime release overflow. Of course, if you have really n bit is the arithmetic logic, the width of the ALU is n bit. For example, in case of 8-bit processor, I just give you example, 8-bit processor such as 8086 or 8088. So then probably you have really only, when it comes to ALU, the 8086 and 88, of course, you have really 16-bit, but 8088 work really also in 8 bits operations. So then of course, really, in case really you add really, when it comes to 8 bits, you know very well that really the maximum number it can carry really when it comes to 8 bits is, you know very well that 2 to the power 8 minus 1. So that means it's 255. So if you add 255 plus 1, what is going to happen that really, yes, there is no mechanism really to reflect the results of the operation. So then usually we usually carry out for that, or probably, and really we can also look at it what is an overflow as well. So then those are really the important things to be considered when it comes to particularly addition. Of course, you should know. So then in that manner, of course, you can see that what we have really, but importantly, any operations is governed by years. You can see 0 is 1. Oh, that means S0 is 1 and S2. So those are clearly important. Depending on really the selection, depending on the combination in S0 is 1, S2, really type of operation to be done will be different. We can see in the subject. Can you go to the other slide, please? So yes, I hope really everybody can listen me. Is that the case? Hello?
Hello?
Yes, sir.
I can hear you.
Okay. So then in that manner, of course, we can design so-called really arithmetic logic unit based on really how really the S0, S1 really manage really the type of operation to be done based on the combination of it. So then you can see that S0, S1 A0 is 1, 0, 0 means really just you can see that what we can see, T is equal A plus Y plus C, that means carry in. So then in that case, what we have really, yes, if at all really, what we can see that all zeros. So then in that case, what is going to happen that really, yes, we have really G is equal A. So then 0, 1. So then you can see that that means really, of course, G is equal A plus B addition, and in case of carry in is there plus 1. So then in case 1, so B bar is equal A plus B bar, right? So then in case carry in is 1, so then A plus B bar. Sorry. So then if it is all ones, then it is going to be decrement. So then A minus 1. So then in that manner, of course, really you can see all are controlled by the combination of values in S0, S1. So then that you have understood when it comes to multiplexer, using the multiplexer, what is it? Then depending on really the number of bits really carries in, so then of course really addition and subtraction and operations can be. So then in this case, what you have to understand, we have only two selections, S0 and 1. So how many operations we can carry out? Oh, maximum of 4 operations, because S0 and S1 means only 2 bits. 2 bits. So then what we have, 0, 0, 0, 1, 1, 0, and 1. That's the most important thing you have to understand. What is that? Really only 4 operations can be carried out. So in this case, you can see the number of functions you can do is limited. So then automatically multiplexer become bigger and bigger depending on. So then you can see that what are the operations we can carry out. In this case is only 4. So then therefore, of course, really complexity will come really, of course, depending on really a number of operations, number of functions, number of tasks to be executed. So same way, of course, you can think about really logical operations you have already understood. So then such as AND, or X, or not. So then in that case, so then we can use S0 and S1 again to do really again how many? Of course, really again limited because of 2 bits. So then 4 kinds of logical operations only we can carry out if you use those. So then in that manner, of course, really you can use really 4 to 1 multiplexer using 2 bits selections. So then you have to understand the fact that really, and so then that really S0, S1 is only 2. Therefore, of course, maximum number of functions, operations, tasks can be done only limited for 4. So then if you want to do addition, subtraction, multiplication, division, and all logical operations, or then we have to think about it, number of tasks to be done. For example, if I ask you to really now design an ALU which can do really, which can perform addition, subtraction, multiplication, division, and O, X, O not. So how many we have? 8. So for in order to do 8, so then 2 is 1 selections not sufficient. So we need multiplexer of 8 to 1. 8 to 1, because we have 8 different operations, 8 different arithmetic and logical operations to be carried. So then a multiplexer will become complex. Multiplexer will become complex. We need S0, S1, S2. S2. Okay, can we move into another slide? So then, as you can see, that really what I said just before, of course, really multiplexer automatically will become complex. Wherever really we have to really do many different levels. Then, in this case, of course, really yes. As you notice that S0, S1, S2 as you really in order to perform different operations. So then in that manner, of course, we can go for complex arithmetic logic unit design. Only matter is really, of course, really how to understand that really what is the number of bits we have really in arithmetic logic unit. So then we know that in that case, if it is ALUs of 8 bits, what we have really chain of sequentially connected adders, full adders. So then you can use really for all the type of arithmetic and logical operations. And then by connecting this kind of, by using a multiplexer, you can control. So that's what you know. So then in the same way, of course, you know that we have already understood one of the primary operations usually you have to do also is the shifter. So that's also we have already understood in a previous lecture. So then So then in that case, of course, we know that the IR is really, of course, will shift to the right or the left, and then sometime rotation. We all want to do this, of course, when it comes to really shifting. So not just shifting. So then we can do really that also, again taking into consideration. Only thing is that, of course, you know that really function of the shifter. I am not going to explain really in details those, because we have already learned in the previous class. So then only thing is that in this case, of course, really 0 is one involved to control the shifting. So based on the combination of values of the 0 and S1 in the multiplexer, of course, really we can do different types of operations. So then in this case, you can see that if at all S0 is 1 0 0, so then you see that no rotation, and then 0 1 means rotate one position. So accordingly, of course, you can see that really available in here, right? So then initially D0, D1, D2, D3. So then rotate one position, and this one is rotate two positions, and this one is rotate three positions. So then rotations can be done. Accordingly, of course, we have to design the shifting and rotation, taking into consideration that. So then normally we call as this one is a bar shifter. Okay, the next slide. Next slides, of course. This one, of course, we are taking back really from the initial diagram. We were trying to explain really in general, taking into consideration. Yes. So then, as I explained to you at the right beginning, register file, of course, really is usually used of registers, as I told, temporary storage, really to read values from the registers or to store back into the registers, depending on whether processor wants to really send data to the register, means really writing, and then reading from register means to do operations. So then for that, of course, we use really in order to really provide from where data comes really to the ALU, of course, based upon really the selection, based on the selection. So then whether we take really data from R0, R1, R2, or R3, so taking into consideration that, of course, really we have used really A select and B select, or A address and B address. So as you can see, select the content of the register to be issued to A data. So then that means really kind of a data bus. So then B data taking really so then the D address is select really to write to data D data. So then like addition or subtraction and so forth. So then in that manner, of course, really you can see if you look at it very carefully. So then we have really A select really to this multiplexer, and the B select is this to this multiplexer. So then as far as you can see that really how these n bits are connected, because n bits is the data coming from the data bus. So if you think about really on a single bit, of course, you should be able to understand. But only thing is that really, yes, based upon A, B select, only the data flow comes really from the particular. So then based on the combination of values, what are the values available in the select, A select and B select, of course, really the data will flow through really these multiplexers. So then in case select A select, so then of course the data comes from this one of these four registers, and then comes really, and then goes through A data, and then here B select. So in case B selected, one of the registers is active, so then go through this multiplexer, and then B data. So then that's more or less really to be understood in this case how the data really are. So then in that manner multiplexers, and then on the other hand, of course, you have to understand the use of decoder to select really so the based upon really the data to be written into one of those registered so then yes, we have to look at it. So then very carefully those as well. So then in that manner, of course, really we can really utilize these maybe what we can call as uh, arithmetic operations from one side. Of course, we understood also shifter. So we can really combine all of them to come up with really, of course, the design in the entire what we can call the operations to be carried out by really uh, uh, any sort of arithmetic logic unit. So then, importantly, one of the important signal really we have to look at it really here is that what we can see is the zero detect. What is the meaning of that? Any arithmetic logic operation is subject to really providing really the results of the operation is zero. So then if at all the results of the operation is zero, so then one of the normally we call in a flag register is a flag. So zero detect, zero really detect. That means really after having done the particular operations, result of the operation is zero. So then this zero detect will be active, will be active. So zero detect initially will be throughout zero. So then suddenly a minus b, a and b values both are same. So a minus b is then result of the a minus b is zero. Means what is going to happen that really, yes, the result of the operation is zero, but z will go from 0 to 1. Z will be active. Zero detect means that, and that is very, very important when it comes to really CPU operations, and very important to understand that on top of really the all other operations so far we learned, and then importantly Z is one of the important one really to be considered as well. So then on the other hand, of course, really there are others other bits as well. So then we have to look at it and to understand how we can really look at it those as well. So then I'm not pretty sure about really n is of course is negative or not, but hopefully it is negative. So then it is indication that really the result of the operation is negative. I don't know, but of course n, yes, is one of the others as well. We can think about it. So then different types of really status of the operations. Of course, we can get really based on really the arithmetic and logic operations we have carried out using ALU. So that is really important when it comes to utilization of ALU. So then data path, it means really not just data, means really result of the operation as such we send to the register. So that really result will be stored temporarily in the register and later on really flushed to the memory or input output device, printer or display and so forth. But importantly, yes, status of the operation. Status of the operation carried out by ALU clearly important. I said really this is usually reflected based on the flag register design. So then arithmetic logic unit is associated with one other important one we normally call as a flag register. So then that flag register is, again, you can see it's a register. It's a temporary storage device. So initially in one state, and then we'll go from 0 to 1 depending on the type of operations, depending on the status of the final result. So arithmetic logic unit does then therefore of course really task assign, addition, subtraction, logical operations and all. On top of that, it also provides really status of the results of the operation, status of the results, such as if at all two numbers deducted resulting 0, automatically implies zero detect really will go from 0 to 1. So then that's basically of course really when it comes to data paths representation, this is really important, and that gives really information, so much of information really for the user, so that really user can interpret what kind of data they have received, in yes, what is the result of the operation, not just as the value, but as well as really what kind of result is produced. As I said, either negative number, parity, and all these things, of course we can design based on the register involved in that case. So then in that manner, of course, really you can really look at it, that really what we can see, that slowly we can see a number of operations to be carried out is increasing from one side, and then therefore, of course, really we have to look at it as well, select. So then in this case, of course, really we can see that number of micro operation to be carried out, and then how these can be really selected, taking into consideration a number of select signals really to be used in this case. So then in that form, of course, really we can go really slowly for complexities when it comes to design, uh, as far as really the data you want to really receive from the processing. Of course, really you have to look at it very carefully. What are the functions really required in order to do these processes? So what kind of signals involved? So that's clearly important. So one of the things that we learned so far, you understood very well. So you can see here, yes, one of the things that really, what is the first operation to be carried out? For example, if you look at from one clock cycle, so then from one first clock cycle, of course, we have to really select data from where the data comes. So that means really from where means address where the data are stored, whether it is stored in R0 register or R1 register, for example, from the original diagram we have seen. So then actually based on the data we have, how we data select, or based on the address given. So then the address means where the data are stored. So then those addresses are very important, put to data into the arithmetic logic unit in order to do the operation. So once operation is carried out, then we have to store the data. So then destination address, for example, D address, is used really to write the data really in another register, or probably in the same register as well. It doesn't matter. As far as really the one source operand is not required anymore, we can use the same register as well. So the result of the function unit is returned to the register while where the D bus. So very important. So then in that case, what we can see here, result of the operation, it goes really all the way really. So then you can see. So then in that case, the result of the operation will be stored in the particular register given by, for example, the D address. So then you can see that we in terms of really, in terms of connectivity really is very important. Why? Because the question is the data will be really propagated through this. So then from one side, we need really source operands. So that's the two addresses required from where the data comes. So then A and B data. So that means really bus A and bus B. Normally we can call bus A and bus B. And then after the operation, after the particular function A plus B, so we must make sure that accordingly the data will be stored in the destination address. So it goes for really the register file given for the given address. So then that given address is, so of course we have already understood from previous slides, that's really taking into consideration select, of course, what kind of address is used really to store data. So so importantly, then we have to understand that really data paths in this case involve basically we can call as really first really we have really addresses. You can say addresses. Addresses means really which register we are going to use really to take the data. So that means really there should be an address from where that data comes. So then that data propagates, data path. So data bus is used really to send data to the arithmetic and logic unit and execute the addition by the ALU, and then send data through the again another bus here. So that really goes to the destination file based upon the address, so then because address is required to select the particular register. So then what it means that, of course, if you look at it to the first figure, you would have understood very well that really we have for 00 is R0 register, 01 is R1, R1 0 R2, 11 is R3. So then from that, of course, we understand that. So how many registers you can have is, so then two address lines, two selections. So only we can have four registers R0, R1, R2, R3. So then 00 means, oh, the address of R0 register. So then we take really A data, and from B we take really R2 for R1, for example. So then 01, and then we send really to R2 register. So then in that case really here we are sending to. But only thing is that these all we have so far considered really within the registers. As I told you at the right beginning, registers are temporary storage which are inside the CPU. So then directly communication with the ALU, but that is not part of really the data we normally read in our normal life. No data we cannot read really from register directly. So what we need really somehow external elements. If you sit inside the CPU, what are the external elements? Of course, the RAM, where you can store data, main memory. So then you know that ROM means CPU can read data, but RAM means you can store data. You can read and write both. So then for the external use means from CPU's point of view, memory and input-output devices such as display, printer, keyboard, all are considered as input-output devices. So then, therefore, data can be written to memory and input-output. Really, we can use. So then, very important to understand the concept of really writing really data externally into the memory and reading data from the external memory is entirely different to the operations with the registers really you have inside the CPU. This is clearly very important to understand. So then the data path representation, of course, really we have to look at it from these two perspectives. So then when it comes to CPU really likes very much really to handle everything internally, because their operations are limited based on the number of registers available inside. So then imagine that if you have 4 registers, you cannot store really any number of data. You can't store 1 gigabyte of data there anyway. So the maximum you can store is really, if the data bus is 8 bits, you know that really only 4 bytes you can store. So therefore, of course, really yes. But why it's like that? Of course, really, only ALU accept really as far as really registers, temporary storage devices constructed within the CPU can be really talk to really each other in the same speed. But when it comes to external memory and input output, their speeds of operations is very slow. So therefore, of course, really CPU will be idle so long, because reading from memory, writing into the memory takes a long time. Clock cycle, you would have noticed in nanoseconds. And then no matter whatsoever you are trying to really write and read from keyboard and display, or writing it, sending to printer, you can't do in those. I'm just letting you know that really. So then, but of course, main memory still is some sort of achievable still really in that way. So then, in that manner, of course, really, what we can understand that really, in order to do these, how to control this, of course, really, we will do really taking into consideration a so-called control word. So then, I mean, it depends on really, of course, how. So then, these can be controlled. So we have to control, as I told you, that really internal operations are entirely different to the external operations. So then sometime really this must be stored. So then controlling, very, very important really when it comes to really the operations to be carried out within the processor. So then for that really, we use really different signals. So then to be a very simple one, of course, really, you can see that RW means really read write. Just to give you really, before I go to others, read write. So then you can see it depends on really, it depends on the write activation. So then usually if read is in 1 or 0, of course write will be in 1. So then if by default it can be 0, so that means by default probably reading. But then if it is active, so then what is going to be what is going to happen, that really is writing data into it. But of course really at the same time we have to read as well, so then from different registers. So then in that way, of course, the functions here given, as you can see, control word, really we have really in this case, you can see that 0 to 15 is what we have. So then how they are really designed, really in this case, is given, sorry, how we can use really to control really the operations. Control means what? Actually, data movement. How we can control, because you cannot really read data without really the operations. The task has been already executed by the AL function unit. So then you cannot store data result of the operation. So therefore, a sequence of operation to be controlled by the control word. So then therefore, of course, really you can see that DA means really selects one register to hold the result of the operation. So then 13, 14, 15, right? So then 0 means really read write. What I'm telling that really the what really each does. So then first bit is 0 RW. What is the meaning of that? If at all really that bit is really in 0, reading, and if it is really a 1, then yes, writing. So then that in the control word, that is the first bit occupied. So we have really 1, and then 1 called as really MD. Okay, then likewise, of course, really all are defined. So then you can see FS. So here you got my point, FS, and then we have MB. So it is about this. So I forgot to tell about MD. MD here. So MD means really the result of the operation. Okay, result of the operation. So FS is the function unit. So you can see it has really 4 signals, 4 bits. So then you should know really number of operations that can be carried out by it. So then how many you should be able to understand by now. So then the multiplexer B is really, of course, really here. So then have really BA. So that means really select the registered from where really the operands come, AA and DA, and then DA means the destination address. So then in that manner, of course, really you can see that control word, based on the control word, of course, really we should be able to. So then that's what we call as really control signals. Then control signals must be activated depending on really data movement. As I told you, writing into the register cannot be done really at the right beginning because there was no operation that has been done by function. So therefore, the sequence of operations will be available, of course, based on the activation of signals. Initially, read signal is activate and then take data from A and BA. That means the reading data using AA and BA. So then of course really based on really, of course, you can see number of bits occupied. So of course really we can take consider number of data. So then of course really based upon that we have to activate really here A and B. So then of course really multiplex B. So then to take really the address and then set the function to be done. And after realizing the function, of course really status of the operation is reflected, is another signal, another 4 signals in this case. You can see that is the status of the operation. So then result of the operation will be stored at the end. So then very important really the sequence of signals to be activated in order to transfer data from registers to the function unit, and at the same time really from the function unit to the destination register, and importantly activation of signals to indicate really what is the result of the operation. So then this is called is a control word. Actually when it comes to CPU, this is about the control unit. We can call control unit, we have arithmetic logic unit we have, and then the status means really, as I told you, flag list. So but we can design our digital system independent of that. So as far as really we should be able to really design our digital system taking into consideration this. So then we can really develop our own. So then in that manner, of course, really we can utilize the control word really to control the complete operations to be carried out. So then each control signal is shown really in this case as you can notice. Of course, what I have explained so far, of course, really available here. So then in that case, of course, different types of functions you can do. So then as you can see, the number of functions depending on that really, of course, we need really number of bits. So then in that manner, of course, really number of functions you to be carried out. So then our code, of course, the signals required really will be really high, or number of bits required is high. Okay, so then in other words, what is the meaning of this code? That's another important matter really we have to understand. What is that? Oh, this means actually you can see this is the function to be carried out. So then if you look at it, so here function unit, so fs. Oh, what is meaning of that? Yes, this implies that really you can see that really 0 0 0. So I will give you really a very simple one. This one is just on the A, but this one is just, you can see, increment value stored in A by 1. Oh, that is 0 0 0 1. Oh, so that means really as far as we have 0 0 1 really entered through the these bits. So fs 2 3 4 5, 2 3 4 5, what is the function it carried out is that increment whatever the value in A by 1. So likewise really, as you can see, that really yes. And importantly, so therefore, of course, we have also one thing very important as well. So if at all we are reading from a register or writing into register, for example, so then of course register selection is based on 0, and if at all we directly adding 1, constant 1 means really a plus 1, a plus b plus 1. So this constant means really we don't have a register. From fly we are adding 1. So then in that case really of course really define based on if at all really MB is in 0 means really values are coming from registers, but if at all it is 1, automatically implies that really that is adding 1. So this we have to do using hardwire so that it works properly, so that really the we have to make sure that really also uh, synchronize accordingly in order to do all these tasks. That is the key point. So control signals are very important in order to execute tasks based on really availability of really data at the time really to be executed, and as well as the data really should flow from register to the function unit, and then from function unit to really the destination file. So this is very important. So then at the first clock cycle, read data from A and B, and the second clock cycle will be sent out the result of the operation to the, for example, I'm telling you. So then within that clock cycle, we have to make sure that really these control signals operate accordingly in order to execute the, in order to propagate the data from register to function unit. So that is the key point. That is the key point. So then that's where really the control signal implementation of control word or control signal is really important, so that sequence of operations will be understood by the CPU how it should work. So then in that way, of course, really you can look at it different types of examples. So then the data path I have already explained verbally. So then we are in the next slide. So then how the operations to be carried out. So by the data path. So then you based on the data path, how the data really move really from register to really do the different types of operations. So for that, control word is very important. So then, as you can see here clearly, you have seen really what the values to be contained, what type of function to be carried out, and then based on that really the writing really will be activated. So that's clearly important to understand. So then R1, R2 and R3 are the operands, and then do the resting and will be stored in R1 destination. So registers involved. So then of course really so likewise of course you can really understand really how it works. Of course R1 means what is the value really, of course you can see here R1 is 001. So then all are understood in how in binary format. So that really yes so they of course really then only really of course so then all are really so just for our understanding only we use letters. So then all will have really kind of really interpretation. So then in that manner yes we can design a simple computer means really of course is a programmable system that gets input in the form of instructions in the memory. Why it is in the memory? Of course, as I told you that really, yes, we want to perform many tasks simultaneously, but CPU, single CPU is not capable to execute many tasks. only single task at a time as far as you have a single CPU. But if you have really multi CPU, so many CPUs, yes, so then each CPU can execute a different task. So then in order to do that, of course, really what we do, what CPU has to do is that really CPU has to take instruction by instruction from the memory and execute one task by task. Oh, that is carried out by using PC, program counter, PC, program counter. So then, program counter is the one really decides to put really the which instruction should go really to the next. It's same as really police constable, no? Traffic police also, no? Traffic police decides which car to be really goes next, particularly in Jakarta, what I understand. So then, same. CPU also like program counter, you have to think about police constable. Same. What is that? Yes, PC decides really which instruction from the memory to be placed into the CPU so that really CPU will execute that instruction. Oh, PC always then directs the next, PC always really has really the address of the memory location of next instruction to be executed. So PC registers is incremental to fetch the next instruction and can be loaded in parallel to jump to the address of another instruction in jump and launch operations. So very important. PC plays the essential role. What is that? So PC controls really sending instruction from the memory to the CPU. And whatever we talked for the up to now was really what is happening inside the CPU, registers and the function unit, also called arithmetic logic unit. But now, so we, as I told you, we want to really execute many tasks simultaneously. So then in that case, we have to have a set of instruction written and stored inside the memory and send instruction by instruction to the CPU to execute really the how to really develop an algorithm and then translate it into an instruction set and store inside the memory. But CPU will take really instruction by instruction using PC, program counter. So then is in charge of controlling the PC to fetch, translate, and activate micro operation sequences to carry out instructions. So very important. So then it is not that really you assume that really all instruction to be executed you can really put inside the CPU. No, it takes one by now. Now, what is an instruction? Okay, what we have understood just before. Just before, we have already understood really what is an instruction, a function to be executed, whether add by one, as you can see. So the code instruction, a plus 1. So as you can see here, a plus 1. So that is the instruction. That is the instruction. Add the value of a, add value stored in a and add 1 really to that. And then we know that operation happens. So then, of course, really, that we really use really and provide the instruction set. So then for that, of course, really it comes to computer architecture. So then there are two things. One, of course, really what kind of really hardware architecture we used, such as CPU is 8-bit width, and then of course ALU we have, and then we have really control unit, we have ALU unit, and then we have register set. And in order to execute tasks, we have to have a set of instructions. So then when it comes to really digital system design, so then instruction set entirely depends on the architecture. What is the architecture? Architecture we have so far talked about it. What is that? So then data path and control really happen. Really how? Of course, taking into consideration type of task to be executed by particularly what is that? ALU and shifter, what we have understood. So then, therefore, of course, really computer architecture, from one side we have really the architecture of the CPU means really register set, arithmetic logic unit, control units, that's really comprises that. But on top of that, that is the model we have. But then we have to have set of instructions which CPU can understand. That called instruction set architecture, or set of instructions we usually to set of operations to be carried out, perform. So then that's called a program. So then that's really we have to somehow really store those set of instructions, not actually I understood just before, of course, really, that's not really all of instructions you can store inside the memory. So then inside registers. So then in that way, yes, the instruction set architecture has three components: storage resources, instruction format, and instruction specifications. So then in that manner, of course, really, you can see really when it comes to storage resources, yes, what we are talking about really in this case. So then when it comes to main memory, yes, we have instructions memory from one side, and from the other side we have data memory, because we have enormous number of data and we have enormous number of instructions. But CPU will execute how? Takes one instruction and relevant data. Data means what? Two operands, and then result of the options will be stored really inside a register. That will happen. Really, you can see registers. You can see registers. What we have here. So then, what we can consider is there's a main memory here. So then, main memory and program counter is the one controls movement of instructions and movement of data into really what? Of course, really. The data. So then, in that way, of course, really, what we really understood that buses really now very important. What is that? Yes. Now I have a simple question. What is that? Okay, we were talking about really the data, and we are talking about buses. So then register 1 and register 2. I have hello. Hello.
Yes, sir.
Can you hear me?
Yes, I can hear you, sir.
Do I have done? What is the time now?
Yes.
How long I have?
Actually, it's
How long I have? I can't remember now.
until 19, sir.
Time is
actually,
up.
the time is up.
Yeah, because we lost a lot of time, no?
Yeah, that's okay.
So, what is going to happen? How do we do the rest?
Oh, that
Rest
is okay.
is really
That's okay, because sir, I think that you have explained the core concept of the CPU in the class. Let me continue in the class. I will continue it in the class about the
that's right.
the explanation. That's okay.
I'm sorry, it is due to technical problems.
Oh,
Technical
that's
problems.
okay. This is technical problem. That's okay.
Yeah. So then we were a little bit nervous at the right beginning, no?
Yeah, that's okay.
Yeah. So okay, do I have to stop now? In that case.
If you
But
if you want,
anyway, yes, I believe. What is it?
oh, that's okay.
Excuse me.
Yeah.
Yeah. Yeah. But anyway, yeah. I mean, to finish it off, really, my talk really today. Yes, just you understood really what we were talking. Of course, really, I can ask a simple question. Yeah. So then yeah, so then we come into the real world. It will be like this. Of course, really, if you understand here, you can see that really we have instruction memory, we have data memory, we have program counter. Yes, either you can think really at home as well. Yes, we have talked about really from one side really the address, and on the other side really data, address and data. Now you understand that really address really of course means where the data are stored. For example, data memory, in this case really you can see 2 to the power 15 multiplied by 60. So 2 to the power 15 addresses. So then 16-bit registers mean 2 to the power. So we don't need to complex like that big. So then of course we can think about 8 bits, right? Okay, my question will be this: what is that? Is actually the data bus and address bus should be of the same width. What is the same width means? If data bus is 8 bits, address bus also should be 8 bit or not? On the other hand, I am asking, of course, really. Now you know really the memory. So memory is usually is very big, usual computer. But the data bus, you have really like, you know very well, really the number of bits in nowadays computer systems. So then what do you think about it? Why really, whether they are must be same or they don't need to be same. So then why? So then yes, very important really, if at all really, if today was very tight, probably you may look at it in the class. So then you can think of really, you don't need to think about 16-bit or 8-bit or whatever. You can, so then actually you can think of really, yes, also 1 bit. So then now same number of bits. So then so computer architecture and instruction set. I had a little bit of problems, and then I'm very sorry for about it, technical issues. Hopefully you got a little bit of idea about in particular data path and really as well as the control word. Those are really two important ones actually when it comes to operations to be carried out by the ALU or function unit you can call. So then and as well as really we have understood also status bits. That's one really of course to be explained quite widely there. And then how these can be implemented hardwired. So then of course that is one of the one part of really this as well, single cycle hardwired control. So then very important, if you try to really implement this kind of single cycle hardwired control, yes, you will be able to understand of course really how the data are propagated, data paths from one side, and how the control signal should be activated. So then how the clock cycle should work. Clock cycle, single cycle means one clock cycle. Within one clock cycle, of course really how you can really do these things. So that means really one clock cycle probably for one thing, and then the second task really likewise of course you can think about it. So then in this case you can see that single cycle hardwired from one clock cycle, expectation needs to execute fetching and executing both should happen. All right, so then hopefully you will get really extended idea from your lecturer. I'm sorry that really I was able to really do only up to this stage. So thank you so much. Any question really, of course, quickly I can answer.
Students, any question?
Otherwise, you can write here in the chat. no chat at all
No,
because
no.
we
I
had
think
really
that's okay.
Mm.
Maybe
we had few problems today.
yeah, I'll ask the students at the class. Maybe we
Of
will
course.
post it in the forums because you also have access to forum if I'm not mistaken, right? Okay, if there is no
I didn't hear the last part.
I'll ask the students
Oh yeah.
to post in the forum, then I will forward
Oh yeah, yeah.
if you that is the
Yeah, okay. Right.
okay.
Okay. Okay. Right. Yes. They might be tired as well.
That's okay.
They
Okay.
might be tired as well.
Okay, students,
Okay.
this is
Then thank you
okay.
so much.
No, yeah, this is the end of
Thank you so
our
much.
guest lecturer. Please give a warm what's it, a warm thank you for Dr. Arosa. Yeah, for the extra question or EDC. If you are still confused, I will you can ask it in the forum in our class, and I will try to forward it to Dr. Arosa if you want to ask. If you have any further question.
That's right. So then
Okay. If no, thank you so much, Dr. Arosa. I'll end this meeting. Thank you so much, students. See you after in the new year. Yeah, happy new year, by the way. Because this is the last week that
yes.
we have.
Thank you so much. Yes, I also wish you really so end of 2022, and then the coming year will be really the most successful one, really compared to previous years. Of course, we will try to improve really all the way.
Okay.
Yes, whatever in coming years, of course, hopefully the coming year will be a successful one as well. Thank you.
Thank you so much, sir. Yeah. Okay.
Thank you
Okay.
so much.
Thank you, sir.
Thank you so much.
Thank you, sir.
for